assumptions that we make here. So when we're looking at these end carbons here, and let me make sure these get highlighted here. So this is an end carbon, and this is an end carbon, just like this one is, just like this one is. So we're going to assume that on this line structure that we have here, that this is where the same end is over here. So this represents that carbon. So we'll just label this as carbon number 1. And we'll label this as carbon number 1. And carbon number 2 we're going to see up here. And then carbon number 3 we'll see down here. And carbon number 4 we'll see over here. All right. So now we can see and visualize where the carbons are located. So this structure here, this line structure, has 4 carbons, just like our expanded structural formula over here and our condensed structural formula over here. So as far as the hydrogens are concerned, these are what we need to mentally account for. So carbon number 1 and again carbon number 4 are very similar because they're the end carbons. And each one of these end carbons contain 3 hydrogens. So I can look at this end here and I can assume 3 hydrogens are going to be there. And I can look at this carbon over here and I can assume that this is also going to have 3 hydrogens. That this over here has 3 hydrogens. And as far as the ones in the middle are concerned, well, those contain, and they're exactly the same, they each contain 2 hydrogens. So here, this carbon number 2 contains 2 hydrogens, and carbon number 3 also contains 2 hydrogens. So again, these are assumptions that we have to understand and have to start getting familiar with. If I were to draw a structure, let's draw a different structure here. So here's a line structure, and we're going to make a couple of assumptions now. Now, as far as this carbon here, I'll label these, I'll number these 2. I'm going to put carbon number 1, 2, 3, 4, 5, and 6. So I know that this particular structure has 6 carbons. Well, let's take a look at the hydrogens, because I'm going to take a look at this hydrogen on the end. So this carbon on the end. So as far as carbon number 1 goes and carbon number 6 goes, they're both on the end, which means that I know these end ones have 3 hydrogens. So here I have 3 hydrogens. And over here at the end on carbon number 6, I also have 3 hydrogens. As far as the ones that are in the middle, those are going to be similar to what we have. Those are going to be similar to what we have up top here, where we have 2 hydrogens here, 2 hydrogens here. So I can assume that carbons number 2, 3, 4, and 5 all have 2 hydrogens apiece. So that's a total of 8 hydrogens, which means that here I have these 8 plus these 3 plus these 3, which gives me a total of 14 hydrogens. So the formula for this particular structure is C6H14, because I'm making these assumptions. And it doesn't really matter how ridiculous the structure looks, but here we just drew it here. So C6H14, if we draw the expanded structural formula, well, let's see here. We're going to go carbon, carbon. So here's expanded structural formula. And then we're going to do the condensed structural formula. So I'm going to start with my N, which is CH3. And then I have 1, 2, 3, 4 CH2s. And then the last one is going to be CH3. So there we have the condensed structural formula. And then for the line structure, well, we're just going to go 1, 2, 3, 4, 5, 6. So here we have condensed, structural, expanded. And one thing you want to watch out for as far as the line structure goes, that the way I count this, I'll redo the way I count this again. So I'm going to put my pen down. And this is carbon number 1 here. Carbon number 1. So 1, 2, 3, 4, 5, 6. But some students will do this. 1, 2, 3, 4, 5, 6. And looking at that, well, let's number these. And this is a structure with 7 carbons, not 6. So we do kind of want to be careful as to how we draw those out. Let's look at some different structures here. So let's see here. Yeah, it really wouldn't matter what the structure is. I mean, I could draw something very small like this, and we should be able to count up the carbons and the hydrogen. So here's an endpoint over here, which means that's going to be a CH3. And I'm going to have this one up here, which is just going to be simply CH2. And then I'll have this end one over here, which is also going to be CH3. And then if we count up all the hydrogens, so there's carbons, there's 3. And as far as the hydrogen goes, so there's 3, 6, 7, 8. So I'm going to put H, 8. So we're definitely making some assumptions. Let me redraw this one. So we're definitely making some assumptions just looking at these line formulas. So just kind of something we do have to get used to. Um, everything that we do for the remaining of organic chemistry, these next 3 units, all of the naming that goes on is based off of these 10 names: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. And this week, today, tomorrow, this is going to be one of the very first things that you absolutely have to memorize before you do anything else. So the first thing you're going to do is memorize these names and memorize these formulas, right? And actually, let me, those are just molecular formulas. So here, we're going to memorize these formulas and these names. And that's your very first priority above anything else you do this week, right? You have homework, practice problems, self-test, studying, review, reading the chapter again, re-watching the video. And the first thing you're going to want to memorize is, again, the names of these structures and their formula. And the reason we do this is that you don't want to fumble around. um, and not know these structures because all of the naming that we do, let's take hexane, for instance. Well, with all of the functional groups that we talked about or that I showed you earlier, and let's go back and look at those functional groups. All of these functional groups take on different names, but they're all derivatives of these first 10 alkane names that we have. So ethers, alcohols, aldehydes, ketones, carboxylic acids, amines, is that they're all based off of the alkane name. We have hexane. I can write hexene, hexine, hexanoic acid, hexanol, hexanal, um, hexanone, hexanamide, cyclohexane. But you'll notice something very familiar here. They're all derivatives of this original alkane name. So if you can't memorize these first 10 names very quickly, that all of this here you're going to struggle with because we don't know. Because I can tell you right now, as far as hexanoic acid goes, if we look at hexane, hexane has how many carbons? Hexane has 6 carbons, which means that hexene has 6 carbons. Hexine, 6 carbons. Hexanoic acid, 6 carbons. Hexanamide, 6 carbons. Is that all of these structures that have hex as the prefix means that all of those structures have 6 carbons. So if I have a structure that's named pentanone, well, because I memorized methane, ethane, propane, butane, pentane, I know that this structure here has 5 carbons. Pentanone, 5 carbons. And I know the structure. This we'll talk about next week. We'll talk about that ONE, uh, which is a particular functional group. But so we really want to concentrate on knowing these formulas and on knowing these names because everything we do is going to be based off of this. All right. So there is a formula. There's kind of there's 2 ways to figure things out. Um, this general formula here, we'll get into that right now. If I go back and if I let's see, let's draw. Okay, so I have a structure here, and let's count up the number of carbons that we have here. So here's carbon number 1, 2, 3, 4, 5, 6, 7, 8. So this has 8 carbons. And we make some assumptions about these endpoints here. So here, I know that this is a CH3, and I know that this is also CH3. And then I have 1, 2, 3, 4, 5, 6 carbons. So I have 6. I have 6 of these CH2s. So if I want to get all of the hydrogens here, well, here we have 3. This is 6. 2 times 6 is 12. So we have a total of 12 hydrogens here plus these 6 hydrogens here. That gives me a total of 18 hydrogens. Right? So I have a total of 18 hydrogens here. So the formula here is CH18. Or that's one way to count up all the hydrogens. This is the other way we count up the hydrogens. And you're going to see this on the exam, right? So you do need to memorize these formulas. They are going to be on the exam. It's not a difficult formula. You don't even need a calculator. So nobody break out the calculator because you don't need it. All right, so we have our formula, CnH2n plus 2, and N is equal to the number of carbons. So let me write this formula, CnH2n plus 2. And where we see this here, this is the subscript, and this is also the subscript. Subscript here, subscript here. N is equal to the number of carbons, which means that if I have a structure, if we look at the structure just above, we know that we have 8 carbons. And that's what N is equal to. So here, N is equal to 8. 2 times 8 plus 2. 2 times 8 is 16, plus 2 is 18. And it matches what we just counted out above here without having to do CH3, CH3, CH2, CH2, without having to do all of that work. Is that here, let's draw another structure. I'm just going to count up the number of carbons here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 carbons, so I have C10. And if we use the same formula, 2 times 10, because that's what N is equal to the number of carbons plus 2. 2 times 10 is 20, plus 2 means that I have 22 carbons. I'm sorry, 22 hydrogens. Okay? So we can use this formula here in order to determine these formulas. If we go, if it's up to 10, I mean, we're really going to be memorizing those anyways. But anything beyond 10, I mean, I can draw a structure here. Let's draw one more. We go 1, 2, 3, 4, 5, 6, 7, 8. So here, 1, 2, 3, 4, 7, 8, 9, 10, 11, 12 or 12 carbons here. So let's use our formula CnH2n plus 2. N is equal to the number of carbons, so that's going to be 8. Two times 8 plus 2. So that's 16, 17, nope, 12. What is not 8? What am I doing? N is equal to 12. So we're going to have 2 times 12 plus 2, and that gives me 26 hydrogens. Right. We can also use it to verify if we actually have an alkane. So not only can we use it to determine the formula of our alkane structures, but we can also use it to verify an alkane structure. That if I were to give you a formula like this, C8, left-handed 8s are horrible. C8, let's do H16. Well, is this an alkane? Well, if I stick that N here, the alkane formula would be 2 times 8, which is 16, plus 2 is 18, that this is not an alkane because it doesn't match my formula. If I have C3H3, well, C3, let's put H4 here. 1, 2, 3, C3H4. So here, is this an alkane? Well, I have 3 carbons, so that's N. 2 times 3 is 6. 6 plus 2 is 8. And it does not match that this is not an alkane. So we can verify if we have an alkane or not, or we can come up with formulas that we need here. All right. These are what we're going to consider structural, what we call structural isomers. Structural isomers have the same molecular formula, but different structural formulas. If we look at the structural formula here, so here I have CH3, and then the next carbon here, actually I'm not going to number these carbons here, I probably shouldn't do that. So CH3, I'll just put an asterisk. The next one is going to be CH2, and the next one is simply just CH, and the next one is going to be CH2. And we'll repeat the process over here. So I have CH3, CH, CH, CH3. So when we talk about they have the same molecular formula. So the same molecular formula means that I have 4 carbons, and we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 8 hydrogens. Is that these molecular formulas are the same. But down below, we see different structural formulas. There's a different expanded structural formula. There's a different condensed structural formula. And we can see that. So anytime that we have 2 structures, they have the same molecular formula, but different structure, we're going to consider those to be structural isomers. Structural isomers. So let's do, how about C? Right? So this is going to be C4H10. And then if I were to draw this, well, let's count up the carbons. 1, 2, 3, 4. So I do have 4 carbons. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H. So again, we have some structural isomers here. Uh, Same molecular formula, C4H10, but you can see that these have a different structure, right? A different structure. So again, we have what we consider structural isomers. Let's see if we can draw some. So here, draw some structural isomers of C7H16. So C7. That's right, we'll get through it. There's just a lot of hydrogen. All right, so here is one isomer. Now, what I'm going to do is I'm going to take this endpoint and I'm going to put it on a different carbon. So here, let's put it on this carbon here. So let me fill the rest up with hydrogens. And I'm going to take that CH3 and I'm going to stick it up here. So we have 1, 2, 3, 4, 5, 6, 7 carbons. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. And these two represent what we consider structural isomers. Same molecular formula, different structure. All right. So when we're looking at these isomers, this is what we consider a branch, right? We can consider it a branch or a substituted group, right? Uh, so when we consider these branches, well, if we take a look at this here, this is C4H10, 3, 6, 7, 8, 9, 10. And if we take a look at the naming, C4, H10, CH3, CH2, CH2, CH3, that the name of that structure is butane. So here, this structure is butane. Because we see the structure, the list told us that we have CH3, 2 CH2s, and another CH3. And that's what we have here. CH3, here's 2 CH2s, and another CH3. And so we have what we consider butane. Let me spell butane. So we have what we call butane. This is also C4H10, but this is our structure of butane. So now we have to put into place some rules in order to name this type of structure, because this is not going to be named butane. So we have to divide this into two separate parts. Is that we're going to view this as this is going to be color here. So we're looking at this. We're going to divide this into two parts. So here, this is what we're going to consider our branch. And then down here, this is what we're going to consider the parent chain. Or we might call it the main chain, right? So it's the parent chain and it's the main chain. And we're going to have to name both portions of this. So if we go back to our naming here, methane is CH4. Methane is CH4. This branch here, it almost looks like methane. but it's missing a hydrogen. This is only CH3, and it's missing a hydrogen. So this group here, I'm going to give it another name as well. So instead of just calling this a branch, we're going to call this an alkyl. An alkyl, and it ends in YL. So instead of calling this methane, we're going to call it, we're going to drop the ANE, and we're going to add YL. So this particular branch is called methyl. And we have different branches, different alkyls that all end in YL. So all of our branches, all of our carbon branches are going to end in YL depending on how many carbons they have. If I have a branch with one carbon, instead of calling it methane, I'm going to call it methyl. Ethane has two carbons. Propane has three carbons. So instead of calling it ethane, we call it ethyl. Instead of propane, we call it propyl. So if I have a structure that looks like this, well, here is my branch. But this branch contains two carbons. So two carbons are in this branch, which means that we're going to name that branch ethyl because it contains CH2, CH3, CH2, CH3. All of your alkyls, notice here, right? CH4, CH3, CH2, CH3, ethane is CH3, CH3. Here, propane, CH3, CH2, CH3, but we removed one of these hydrogens. So all of your alkyls will always have just one less hydrogen than the alkane. So this is how we're going to identify those carbon chains. And then we're going to take a look at the parent chain. So the first thing we're going to do, so the first thing is we identify and name the alkyl branch. And secondly, we're going to name the parent chain. So here in this top one, well, we know that this is methyl. And as far as the parent chain goes, I'm going to count the number of carbons here. 1, 2, 3. And any alkane that has 3 carbons is named propane. So now let's put both of those together. First, we identify, name the branch, then the parent chain. So here we have methyl propane. Let's take a look at this next one down here. Let's name the branch first, and the branch has 2 carbons. That's going to be named ethyl. So this is ethyl. Let me make one adjustment here. I'm going to erase this one. Yep, let me erase that one. And we'll put this to a 3. All right. So we have ethyl, and then if we name the parent chain over here, is that we're going to have 1, 2, 3, 4, 5 carbons, and anything that has 5 carbons is named pentane. So this is ethyl pentane. All right, so let's see. You know what? I'm going to push pause here for a second. So let's go ahead and practice some of these. Yeah, something that we definitely have to go over is, let's see, how about, I'm going to write something like this. Then we have, let's see. All right, so we have 2 different structures here, and I'm just going to go ahead and circle the branch for you guys. So we have this one has a branch over here, and this one has a branch over here. And then I'm going to go ahead and circle the main chain. So here is our main chain. Here is our main chain. So we're going to name the branch first, and then we're going to name the parent chain. So CH3, this is our alkyl, and this particular alkyl is named methyl. So here, this is methyl. Then we're going to count the carbons, 1, 2, 3, 4. 5 carbons in the parent chain, and 5 carbons in the parent chain is named pentane. So here, the parent is named pentane. And then when we put them together, we can call them methyl pentane. And then we could do the same thing here. So here we have our branch again, and this branch name is methyl. And then we're going to have the number of carbons, 1, 2, 3, 4, 5. This also has 5 carbons, and that's going to be named pentane. And then when we put them together, we're going to have methyl pentane. So this kind of presents an issue here because we can see both of these structures, and they definitely have different structural formulas. Our molecular formula, the molecular formula is still the same. We have 6 carbons and we have 14 hydrogens. This is 6 carbons long So we have 6 carbons. This is 14 hydrogens. And let's just verify that, right? So we have 1, 2, 3, 4, 5, 6 carbons, all single bonds. So I know it's an alkane. And then if we count all the hydrogens, we have these 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. And the bottom one's also going to have 14. But we can see, so same molecular formula, different structure. So these are isomers here. And because of that, they have to be named differently. Is that here, I'm going to number these carbons. This is going to be carbon number 1, 2, 3, 4, 5. And I'm only numbering the ones in the parent chain. Right? So here, there's 1, 2, 3, 4, 5. This branch, this alkyl, is located on carbon number 2. So we're going to signify that in the name. And we're going to put that this is 2-methylpentane. Well, this methyl branch on the parent chain over here is on carbon number 3. So we can call this one 3-methylpentane. So we have 2-methylpentane and 3-methylpentane depending on the location of this alkyl branch. So anytime that we come across these now is that we're going to use the number of carbon that those are on, that alkyl's on, in order to finish naming the structure. So I'm going to draw just one more here. We still have some more to practice with. CH3. All right, so here we have our branch. And here we have our parent chain. So the name of this branch is methyl, and the name of this parent chain is going to be pentane. So again, we can put those together. This is methyl pentane. When you number this, there's no such rule as we have to name this or number these from left to right. The way we number it, there's a priority to these carbons. And the priority comes with the branch. And that's how we decide how to number these this alkyl branch. You want the branch, the alkyl, to be on the lowest numbered carbon you could possibly put it on. So if I number these, I'm going to number this one way real quick. 1, 2, 3, 4, 5. If I write it this way, the methyl is on carbon number 4. But since there's no rule that says that's the only way to number it, I could number it this way. 1, 2, 3, 4, 5. And if I do that, then my methyl is on carbon number 2, which is identical to this one up here. So all we've done is really just flip this. We've really just flipped this in in physical space here. I'm gonna turn my camera on real quick. Let's see. All right, so I have my camera on. Use some of my wife's pin here. So this is just kind of what we're thinking here. So magic trick. Watch this. It's a great magic trick. Look, my hands are cold though. All right, magic trick. Everybody ready for this magic trick? I know it's on camera, but trust me, it's going to work. I promise you. It's a great magic trick. So this is a blue gel pen. See that? Everybody, blue gel pen. Watch this. Watch this. Ready? Blue gel pen. Watch this. Ta-da!
Whoa!
It's still a blue gel pen, right? Just because I flip it around in physical space doesn't change the fact that it's still a blue pen, right? It's still a blue pen. So that's all we did here, is that when we look at these two molecules, this one up here and this one up here, all we did was actually just flip it around in physical space. So you want your branch, so there is no rule. There's no rule that says that you have to number these right to left, left to right. We decide on the numbering system by determining the lowest numbered carbon we can possibly have for that branch. In, let's see here. I need to draw some of these in. I'll let you know what this looks like. So if I have 5 carbons here, so 1, 2, 3, 4, 5. So here's 5 carbons, and here's my CH3, right? Is that we can look at this. If I were to redraw this here, so we got CH3, that's my N one. CH2, hi sweetie. CH2, CH, CH3, and then we have CH3 here. So these two represent the same thing, right? Here's my branch. Here's my main chain. The main chain has 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. I want my branch on the lowest numbered carbon, so I'm going to number this 1, 2, 3, 4, 5. And because this is methyl, I have 2 methyl pentane. But what we have here is this is what we're going to see in line formula. So anytime we just see this little branch just sticking out like that, that's going to be considered a methyl. Right. So here we're going to identify this. This is my branch. This is the same thing as me writing CH3. It's an endpoint, so I know there's 1 carbon there, and I'm going to assume there's 3 carbons surrounding it. So that's my CH3, and that is my methyl branch. Well, now I have to decide where my carbon number 1 is. It my carbon number 1 on the right, or is it on the left? Well, let's try both numbering systems. This is going to be carbon number 1, 2, 3, and if I do this, I'm going to have 3 methyl. Well, let's try numbering it the other way. 1, 2, 3, 4, 5. I'm going to have 5 methyl. So I guess that numbering system won't work out. We'll go back to the other numbering system. So we're going to go 1, 2, 3, 4, 5, 6, 7. So I need the alkane name for 7 carbons. We're going to see that here, alkane, here it is. 7 carbons, it must be heptane. I have a carbon on our methyl group on carbon number 3, so this is 3 methyl heptane. So 3 methyl heptane is our name for this particular structure here. Oh, how about, I don't want to run out of room here. Um, all right, so here we have another structure. I'm going to circle our branch. So here's the branch. And here's our main chain. And just by visually looking at it, I'm not going to write them down anymore, but I can clearly see that carbon number 1 is going to be over here. So there's carbon number 1, 2, 3, 4. And this particular branch has a carbon here, and it has a carbon here. So it's got 2 carbons there. And any branch, any alkyl branch with 2 carbons is named ethyl. So I know the name of this. I have a 4-ethyl. And let me continue to number these. So this is carbon number 5, 6, 7, 8, carbon number 9. And any alkane with 9 carbons is called nonane. Nonane. Here, 4-ethyl, nonane. Right? And we can name that structure there. Let's see, how about a different structure? How about, because it is possible to have two branches. You can have 3 branches, 4 branches. So we can definitely have multiple branches on our structures. So here, let me circle our branches. And both of these branches represent CH3. So these are both going to be methyl branches. And let's see, let's number these carbons first. So here, if I number it this way, 1, 2, 3, 4, 5, 6. Let's look at the branch numbers. The first branch would be this carbon here. Oh, that screwed that up. Renumber them. 1, 2, 3, 4, 5, 6. And then I have my 1 branch here, 1 branch here. The first branch would be at carbon number 3, and the second branch would be at carbon number 5. All right. Well, let's go ahead and number it the other direction. 1, 2, 3, 4, 5, 6. The first branch would be at carbon number 2, and the second one would be at carbon number 4. So those values are smaller, so we're going to use that particular numbering system. So we're going to use that particular numbering system. In order to name the structure here. So we have, I'm going to write a list of what we have. So on carbon number 2, we have methyl. And on carbon number 4, we have methyl. And anything with 6 carbons long is going to be named hexane. Well, we need a shortcut here. So instead of writing 2-methyl, 4-methyl, well, because they're the same, we're going to use a Greek prefix, and di, meaning 2, because we have 2 methyls, we're going to use this shortcut here. I'm going to write the number 2 for 1-methyl, a comma, the number 4 for the other methyl, and then I'm going to put in this little hyphen here. And I'm going to write dimethyl, as opposed to writing 2-methyl, 4-methyl, we can make a little shortcut and we can write 2,4-dimethyl. So then we can put all this together, and if we write it out, we're going to have 2,4 dimethyl hexane. If it was 3, we'd have trimethyl, 4, tetramethyl. Right? So depending on how many of those branches we have. But as long as it's the same, we can use those Greek prefixes in order to do it. We can have another situation. How about, let's put this here, and then how about put this here. So now I have 2 branches, but both of these branches are different. One branch has 1 carbon, the other branch has 2 carbons. So one of them is methyl and one of them is ethyl. So here, let's identify them first. So this one here is going to be methyl. That's my CH3. And this one happens to be ethyl. CH3, CH2. CH3, CH2. How do I know this? Because we went over assumptions that we make with line formulas, right? So now comes time to number this. So let's start with our numbering system here. So I'm going to number it one way. 1, 2, 3, 4, 5, 6, 7, 8. If I number it this way, my branches are on carbon number 3 and carbon number 5. If I number it the other way, 1, 2, 3, 4, 5, 6, 7, 8, my branches are on carbon number 4 and carbon number 6. Right? The other way is lower, so we're going to stick with this original numbering system that we had in place here. So 1, 2, 3, 5, 6, 7, 8. All right. So I'm going to make a list here. On carbon number 3, I have methyl. On carbon number 5, I have ethyl. And an alkane that's 8 carbons long is named octane. Before I put this together, I do need to let you know, when you have branches that are different, these are written alphabetically, not by the number carbon that they're on. The numbering system, yes, we use the lowest numbered carbon we can find. But as far as actually naming it, we're going to put the branches down in alphabetical order. Ethyl before methyl. So this is 5 ethyl, 3 methyl octane. Alphabetical order. Ethyl before methyl. So notice that between numbers, we use commas between numbers, and we use hyphens, right? We use these hyphens between the number and the word. Hyphens between a number and a word, commas between just numbers themselves. Let's see, how about... All right, so here's the structure here. Let me circle our branches. So here I have a branch with 2 carbons, branch with 1 carbon, branch with 1 carbon. So this one is ethyl. This is methyl. This is methyl. I can clearly see that this is going to be my numbering system. 1, 2, 3, 4, 5, 6. I'm going to write these down. On carbon number 2, I have methyl. On carbon number 4, I have another methyl. And on carbon number 3, I have an ethyl. Well, and then 6 carbons long, I have hexane. Well, let me go ahead and I'm going to combine both of these here to say 2,4-dimethyl. So now I've kind of gotten rid of this. So I have 2,4-dimethyl and I have 3-ethyl, and I need to put this in alphabetical order. We do not use and I'm going to put Greek prefix. Do not use the Greek prefix. Do not use Greek prefix for alphabetical order. Do not. This is still ethyl before methyl. So if we write the name of this, this is 3-ethyl. 2, 4 dimethyl hexane. It is still ethyl before methyl. We don't consider that Greek prefix. I think a couple more that we haven't seen just yet is propyl. So let's draw propyl. So here is propyl. So notice the carbons here. I have one carbon here, another carbon here, another carbon here. So that's 3 carbons. Propyl from propane. And notice this here. Let me clean some of this up here. CH3, CH2, CH2. And if we look at our structure here, we can identify that here as the end is CH3, this is CH2, this is also CH2. Right? If we're looking at these structures here, this is CH3, CH2, CH2, CH3, because we make those assumptions. One thing we haven't talked about is if I do this, this here is no longer CH2. Is that here, because I add a bond, and let me rewrite this a little bit lower so we can understand and see this. So this is CH3, CH2, CH2, CH3. If I add a branch here, CH3, let me expand this out for you so you guys can really see it here. So CH3, CH2, CH2, CH3. So we're talking about this carbon here, this carbon here. If I add a CH3 to it, well, this carbon now has 1, 2, 3, 4, 5 bonds. In order for me to add a CH3, I have to get rid of a hydrogen. I have to get rid of a hydrogen. So that here, this carbon here is CH3. H. And then if I look at this carbon here, this is a CH. It's not a CH2. Right? So just something to be aware of when we're looking at all of these structures here. All right, so back to naming this. I have, again, just as a reminder, let's just go back. CH3, CH2, CH2. The name of this branch here, so CH3, CH2, CH2, that this is propyl. So that particular branch is propyl. How many carbons long is this? 1, 2, 3, 4, 5, 6, 7, 8 carbons long. Where's carbon number 1? 1, 2, 3, 4. 1, 2, 3, 4, 5. This is carbon number 1. 2, 3, 4. So this is going to be 4 propyl octane. 4 propyl octane. And now to finish just this section of it, I'm going to draw one more structure. My rendition of a pterodactyl. No, I'm just kidding. We have branches here. Probably one of the more difficult branches to understand. And I'm actually going to draw this out in condensed structural formula as well. So here we have CH3, CH2, CH2 is going to be just carbon, CH2, 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 CH3. And then down here we have CH, CH3, CH3, and above here we have CH2, CH2, CH3. All right, so let me clean this up a little bit. All right, so here it is in line formula as well as condensed structural formula. And what I want you to notice these two branches here. And notice how the hydrogens are bonded together. In this one up here, we have CH3, CH2, CH2. And if we go back to our alkyls, you'll see CH3, CH2, CH2 is propyl. So this particular branch is named propyl. Well, let's look at the pattern down below. We have CH3, CH, CH3. Well, that's not propyl because propyl is CH3, CH2, CH2. CH3, CH, CH3 is isopropyl. So this particular branch down here is what we consider isopropyl because of the way it's bonded. So notice here how this is what it looks like in line formula, and this is what it looks like in condensed structural formula. Is we kind of have that Y shape that's attached to that, the difference between our propyl and isopropyl. So let's see, 1, 2, 3, 4, 1, 2, 3, 4, 5. So carbon number 1, 3, 4, 5, 6, on carbon and alphabetical order. As far as Greek prefixes, mono, di, tri, tetra, penta, Greek prefixes we do not use. But iso is not a Greek prefix. That's the name of this alkyl. So alphabetical order says that we're going to do 4 isopropyl, 4 propyl octane. So 4 isopropyl, 4 propyl octane. And that's what we would name that structure there. I think just maybe one more example. This is just really regarding the numbering system. If I put 2 branches here like this, so I'm going to put 2 branches on this structure. Both of them happen to be methyls. They're both on carbon number 2. If I'm going to write this out, I'm going to write 2, comma 2. So even though it's the same, even though they are the same alkyl on the same carbon, I'm not going to write just simply 2-dimethyl. I'm going to write 2,2. So even though they're the same number, it's not redundant to do that. So it's going to be 2,2-dimethyl hexane. 2,2-dimethyl hexane. Right? So we just want to make sure that we're clear and that we, in fact, do have 2 of them on there. Oh, I think we've done quite a bit of naming. I think that's probably, these are practice problems in your book that you guys can get to. I don't think you have a problem getting those there. So we do have to be able to name these, though. I'm going to draw these structures out. When we're drawing these structures out, I work from the back here, the end of the name. So I'm going to draw it in this particular direction. Right? I can't do anything with the branches until I actually have the parent chain. And then we can just simply add in the branches. So hexane, well, hexane, if you go to your list of alkanes, hex means 6. So this is going to be 6 carbons long. So A is going to be 1, 2, 3, 4, 5, 6. And because I'm drawing it out, I get to choose where I want carbon number 1. I want carbon number 1 to be on the right. So on carbon number 2, I'm going to put a methyl. And on carbon number 3, I'm going to put an ethyl. So there is 2-methylhexane. Say, but Alex, mine doesn't look like that. I drew mine different. I drew mine this way. You know what? It's the same exact answer. These are both the same structure. They're both 3-ethyl, 2-methylhexane. Let's move on to number B. So heptane, I'm going to draw 7 carbons for heptane. 1, 2, 3, 4, 5, 6, 7. I'm going to be, carbon number 1 is going to be on the left-hand side this time. So this is going to be my carbon number 1. Carbon number, so 2,2,5 trimethyl. So that's 3 methyl groups. One on carbon number 2, another one on carbon number 2, 3, 4, and one on carbon number 5. Let's do C. So this is going to be B. These are both A. So let's do C. Nonane 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to do carbon number 1 on the right-hand side this time. So on carbon number 4 and 6, there's a diethyl. 1, 2, 3, 4, 5, 6. So there's a diethyl. There's 2 ethyls on, oh, that's carbon number, there we go. 1, 2, 3, 4. Carbon number 4 and carbon number 6 get a diethyl. And on carbon number 6, there's just simply a methyl group there. Let's do D, octane, 1, 2, 3, 4, 5, 6, 7, 8. So 8 carbons. Carbon number 4, there's an ethyl. And I want carbon number 1 to be on the left-hand side this time. So 1, 2, 3, 4. So carbon number 4 is an ethyl. And on carbon number 4 is also an isopropyl. So that's that Y-looking structure. And here we have 4-ethyl, 4-isopropyl octane. And let's see here. All right, so when we have, just kind of keep an eye out. When we're talking about the parent chain, so the parent chain is the longest continuous, and this is really a key word here, the longest continuous carbon chain. The longest continuous carbon chain. Don't get tunnel vision when you're looking at this. Is that most students will look this direction or this direction. They go left to right, right to left, and they go, okay, Alex, this is hexane. And I say, no, this is definitely not hexane. But Alex, count it, 1, 2, 3, 4, 5, 6. 6 is hexane. I said, yes, 6 is hexane, but this is definitely not hexane. So we don't want to get tunnel vision looking at these structures. The parent chain is the longest continuous carbon chain. So whether we count sideways, backways, frontways, whichever way, the longest continuous carbon chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is nonane. Nonane with a methyl on carbon number 3 and a methyl on carbon number 6. Right? So this is 3, 6, dimethyl nonane. All right? So don't get tunnel vision and only look right to left or from left to right. Right? So just kind of be cautious with that as well. All right. So this will bring us over into what we consider another type of alkane structure. These are what we call cyclo alkanes. Right? So cyclo alkanes, so sometimes these structures can form ring structures, right? And here we can see we have 3 different, this is our expanded structural formula. So this is expanded structural formula. This is condensed structural formula. And we're not going to call these, because they're shapes, we don't call them line structures. They basically are line structures, but we call them geometric formulas. When you're doing your labs, be cautious of that word, geometric formula, because students will draw this when they're only requiring this or this. But students get they get so used to drawing all these structures. They've just got to be careful in the lab. But you can see that they form shapes here, and we're going to use a prefix of cyclo here. So whatever the alkane is, then we're just going to simply use cyclo, right? So 4 structures here. So if we look at this particular structure, there's 4 carbons here, 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. And we go back to our list here. We see that 4 carbons is butane, but because it's a ring structure, we're going to add the cyclo to it. So it'll be cyclobutane. We can put cyclohexane, cycloheptane, cyclooctane, cyclodecane for however many carbons that we see in that structure, and that's what we see down here. So here, right, 5 sides, 5 carbons, cyclopentane, 6 carbons, cyclohexane. If we had 7 carbons, it'd be cycloheptane, cyclooctane, and so on. So these structures here, oh, you know what? And for these alkanes here, this formula, CnH2n plus 2, does not work. Does not work for ring structures. Doesn't work for ring structures. All right. So we can also have branches on these, right? We can definitely have branches on them, and we name them in alphabetical order, and we're also going to number it the same way. So here, you notice that this is carbon number 1 up here. Carbon number 1 is not necessarily the top carbon, right? Is that if I redraw this down here, 1, 2, 3, 4, 5, 6, and let me put ethyl over here, and then I'm going to put propyl over here. So here I have one branch, this is ethyl, and here I have another branch, and this is carbon number 1, 2, 3. So there's 3 carbons there. So this is definitely propyl, and this is ethyl. Well, in order to number these, we're going to use alphabetical order. Well, ethyl comes before propyl. So ethyl is going to be, this carbon here is going to be carbon number 1 because ethyl comes first alphabetically. Now, there's no rule that says you can only number clockwise or counterclockwise. You take the shortest path to the next branch. So I could count this way. And if I count it that way, we're going to go carbon number 2, 3, 4, and this would be carbon number 5. But if I take the shorter path and number it this way, then propyl ends up being on carbon number 3, and we have 1 ethyl, 3 propyl, cyclohexane, right? So whichever way that I do, so let me redraw this here. But instead of, so 1 methyl here, I'm going to put 1 methyl over here. So I have 2 methyls here. This is going to be carbon number 1, and I'm going to take the shortest path, and I'm going to go this direction for carbon number 2, right? Because that is the shortest path to the next branch. If I were to draw this upside down, carbon number 1, carbon number 2, right, is that here, if this is carbon number 1, this is carbon number 2, and again, I take the shortest path. So all of these are all 1,2-dimethylcyclohexane, right? A new branch that we have is our halogens. Halogens are all going to be named. So we have a few halogens here. So we have fluorine, chlorine, bromine, and iodine. So fluorine is going to be fluoro, and then we're going to have chloro, bromo, and then iodo. So if I draw a structure like this, and I put, let's put isopropyl here. Isopropyl, what? No, let's not use isopropyl. Let's use ethyl. Here's ethyl, and here is chlorine. Okay, so alphabetically, chlorine comes first, ethyl comes next. So here, carbon number 1 is going to be where my chlorine is at. Carbon number 3 is where ethyl is at, so I have 1 chloro, 3 ethyl, cyclohexane. And then if I were just to do this, I think there's one more example we need to understand here, and that's when we simply just have one branch. So here, this is bromo cyclohexane. And it's not one bromocyclohexane. This is simply just bromocyclohexane. I know where carbon 1 is at, and carbon number 1 is right here. Because this is the only branch on the cycloalkane, there's no reason to signify that it's 1. Because even if I turn it and I put the bromine somewhere else, it doesn't change the fact that this is carbon number 1. So I don't need to keep stating that this is carbon number 1, because that's all it could be. It can't be anywhere else but carbon number 1, because it is the only branch on that cycloalkane. So bromocyclohexane. Right? We see those examples down here. Ethyl cyclohexane, because it's always just on carbon number 1. Methyl cyclohexane, because it's always just going to be on carbon number 1. So when we have just one of those groups attached to it, there's no need to actually write down carbon number 1. Now we come to isomers. I think this might be a little, I want to explain so that you're going to see something like this on your homework. So this is telling me to draw 4 isomers of cycloalkane. So there's my first clue here. It has to be a ring structure. So 4 isomers of a cycloalkane that has 6 carbons, 12 hydrogens. Okay, well, let me draw one here. This has 6 carbons and 12 hydrogens. And just to make sure we understand the placement of these hydrogens, let's go back to this expanded structural here. Each one of these carbons contains 2 hydrogens. So 2 hydrogens here, 2 here, 2 here, 2 here. There's 2 here, there's 2 here, 2 here, 2 here, 2 here, and we can understand that. So when we're looking at this structure here, I count 2, 4, 6, 8, 10, 12 hydrogens, 6 carbons, but now it wants another isomer. It doesn't say that I need a 6-ring structure. I just need another isomer. I need something else that doesn't look like this. So what if I were to draw this? Well, this only has 5 carbons. 1, 2, 3, 4, 5, but the formula is asking me for 6. So what if I do this? And I put a methyl on it. Well, now I have 2, 4, 6, 8, 9, 10, 11, and I also have an imaginary one right here, giving me 12. So this is another isomer. All right, let's draw some more isomers. How about, well, I only have 4 carbons, but it is asking me for 6. So now I have 6 carbons. I can also draw this. Nobody says I have to have 2 branches. Why don't I just put one branch. And there's another isomer, right? Let's see how we can go down to cyclopropane. We can go 1, 2, 3. So that gives me 6 carbons, or maybe I can do something like this. Maybe I can put an isopropyl on it. That's also 6 carbons, right? So there's a bunch of isomers we can put there by just putting branches in and making our alkane structure smaller. I guess we can draw some of these out. Let's draw. Let's see. Let's do this one here. Let's do D. If we're looking at D, we need to start from the parent chain first. So the parent chain says pentane, but it says cyclo. So let's draw cyclopentane, which is 5 carbons. So 1, 2, 3, 4. Yep, I have 5 carbons. And 1, dichloro. 1 chlorine on carbon number 1. Oops, that's not. And another carbon on chlorine number 1. Let's see, cyclobutane. So we'll draw cyclobutane first. Carbon number 1, and I choose where to put carbon number 1. I'm going to put carbon number 1 down here. Bromo, and carbon number 2, we'll make this one over here carbon number 2 with a methyl group. All right. So when you're drawing these out, you get to decide where carbon number 1 is. Maybe I don't want carbon number 1 at the top. Maybe I want carbon number 1 at the bottom. Maybe I want this to be carbon number 1. And it's still the same structure. This is not an isomer, is that these are equal to each other. These are not isomers. They are the same structure. All we did was just spin it upside down, right? But it's definitely the same structure. Remember my pen trick there, right? Just because I turn it doesn't mean that it's not the same structure. Let's see. I think this one's on your homework, but this one really gives you guys gives most students a lot of trouble. When we're looking at this, I noticed that we kind of have to draw this out in order to name this one properly. So here, it says we have 3 CH3s. So here's one CH3, and then I noticed this carbon by itself. So I'm going to attach it to this carbon, and I'm going to put another CH3 on it, and I'm going to put another CH3 on it. Then I have CH2, and then I have CH3. So when you're doing your homework, this one can be drawn out because now I can look at it and I see this is butane with 2 methyl groups on here. Here's a methyl, here's a methyl. So we have 2,2-dimethyl butane on this one here, right? So just some, as I think there's one of the homework problems going to be pretty similar to that. I guess we could name these. So let's go ahead and name these real quick. 1, 2, 3. Oh, okay. So this is an issue where if I count here, 1, 2, 3, 4, 5. But is that the longest chain? Because I can also count 1, 2, 3, 4, 5, 6, 7, right? And that's definitely a longer chain. I just have to decide. My numbering system. So 1, 2, 3. My first branch is going to be at carbon number 3. If I decide to number it 1, 2, I notice that I have a branch on carbon number 2. So I think I'm going to go with that direction there. So let me number this, and we'll say carbon number 1, 2, 3, 4, 5, 6, 7. Which means that here I have a branch, branch, branch. Carbons, ethyl first, so this is ethyl. So I have 5 ethyl. I have 2, 5 dimethyl heptane. The next one is cyclohexane, 1, 2, 3, 4, 5, 6. This is methyl, this is methyl. So I'm going to have 1, 1, I'm sorry, ethyl, 1, 1 diethyl cyclohexane. Because of these two ethyl groups here, this is going to be carbon number 1. Let's see, 1, 2, 3, 4, 5, 6, 7. Isopropyl, this is methyl. Isopropyl before methyl. So 4 isopropyl, 2 methyl heptane. Okay, so that's how we would go and number all those there. I think we'll probably skip these two here because we do need to keep going here. So this is a really lengthy chapter. So this is our first reaction that we need to understand. So this is reaction of alkanes. We're going to see another reaction, but that's going to be the reaction of alkenes, which is different. This is the reaction of alkanes. So these are what we consider combustion reactions, right? Usually it's just oxygen in the air, and either with some heat or some light, we can get this reaction moving here. So, and it's always the same thing. It's some alkane, plus we take some oxygen, we're going to get CO2, plus some water, plus we get energy, right? So we have alkane plus some O2. We're always going to get carbon dioxide plus some water, plus we're going to get some energy. In the reaction, right? It always ends up the same way. It doesn't matter what the alkane is, whether it has 5 carbons, 10 carbons, 20 carbons, it's alkane plus oxygen. You're going to get carbon dioxide plus water plus some energy. So if I had so here's my alkane structure, right? My alkane structure has 1, 2, 3, 4, 5, 6, 7. I have 7 carbons there, so it's going to be this alkane plus some oxygen. I'm going to get carbon dioxide, plus I'm going to get some water, plus I'm going to get some energy from that. So this is an unbalanced equation, right? I have kind of written this out here, but it is unbalanced because over here, let's look at the formula over here. This is going to be C. This is a good time for us to practice this. Cn H2n plus 2. I have, again, 1, 2, 3, 4, 5, 6. I have 7 carbons. N is equal to 7. 2 times 7 is 14, plus 2 is 16. And I have my molecular formula. So I notice I have 7 carbons here and 1 carbon here. You don't have to make any lists here, right? I want you to do it in this particular order. First, you're going to balance the carbons. Second, you're going to balance the hydrogens. And third, you're going to balance the oxygens. Do it in this exact order every single time, and you don't have to make any lists. So balance the carbons, I'm going to need to put 7 here. Balance the hydrogens. 16, I'm going to put an 8 over here. Now I need to balance the oxygens. 7 times 2, there's 14 oxygens over here, and there's 8 oxygens over here, 22 oxygens. And there's my balanced chemical reaction, right? But again, it doesn't really matter what the alkane is, right? I can make a smaller one. So let's do, how about C3H8? Here's my alkane. I'm going to do a combustion reaction, which means I'm going to add oxygen, and I'm going to get carbon dioxide, plus I'm going to get water, plus I'm going to get some energy. Well, let me balance the equation now. I need 3 carbons. I'm going to need 8 hydrogens. I have 6 oxygens here, 4 here, which means that I need 5 here. So here's my balanced chemical reaction. But all combustion reactions again deal with just, these are how we deal with reaction of alkanes, right? Combustion reaction of alkanes. And the next reaction we're going to learn are halogenation reactions, right? Uh, but again, there's 2 types, right? So this is halogenation of alkanes, right? Halogenation of alkanes. So here's an alkane, methane, plus a halogen, and we get this halogenated alkane, plus we get this hydrogen halide. It's always the same reaction, is that it doesn't matter what the alkane is. Let's do, how about, here's my alkane. We'll use cyclopropane. So cyclopropane, this time we'll use, how about bromine? Cyclopropane plus some bromine. So here, notice up here that we broke the Cl2 up. So this is Cl, Cl, and what do? We broke it up. One of the chlorines went to the carbon, and the other chlorine ended up with the hydrogen that we removed from the alkane. And the same thing happens here. So here, we're going to break up that bromine. So the bromine is here. We're going to break this bromine in half. We're going to put 1 on the bromine. So now we have this is my halogenated alkane, because again, we're using halogens, right? Halogens are your fluorine, bromine, chlorine, iodine, right? Those are all of our halogens. So here I have my halogenated alkane, plus I need a hydrogen halide. And here's my halogen. And they always will end up the same way. Here's my alkane. Let's use fluorine this time. I'm going to get my halogenated alkane plus my hydrogen halide. Right? So those are our 2 first reactions, combustion reactions, and then halogenation. But halogenation of alkenes. We're going to see halogenation of alkenes in a little while. We've already covered this nomenclature for our alkanes. Yep. So this is what we're going to consider our first functional group. This is alkenes. So alkenes, and notice the E-N, right? Not alkanes, but alkenes. Alkenes have a double bond to them. Somewhere in there is a double bond. And our formula in order to determine alkenes is CnH2n. For alkanes, it was, sorry about that. For our alkanes, it was CnH2n plus 2. So these are alkenes. Right? So if I have an alkene that looks like this, let me put a double bond in here. So there's my double bond. And let's count the carbons here. We have 1, 2, 3, 4, 5, 6. So N is equal to 6. Well, let's put that in this formula here. So if N is equal to 6, 2 times 6 is 12. So I have 12 hydrogens. And this is my molecular formula for an alkene. Right? Then we have alkynes, and here again we have another formula. And again, you need to memorize these formulas. All three of these formulas are going to be tested on. Right? If I have an alkyne, let's do, let's see. Right? We have 4 carbons. N is equal to 4. 2 times 4 is 8. Minus 2 is 6. So here's the formula for my alkyne. Right? If we want to see this in line formula, is that this is carbon number 1. At the end of the triple bond is carbon number 2, carbon number 3, and carbon number 4. Right? So notice on this one, there's no up, down when we initially started because of that triple bond there. So just take note of that. Is that here, carbon number 1, at the end of that triple bond is carbon number 2, then we have carbon number 3, carbon number 4. So we're going to use the ENE and the YNE in order to name these structures here. So we're also going to use a numbering system here. So here we have, let me number these, carbon number 1, 2, 3, 4, and 5. So this is what we're going to call 2-pentene. Not pentane, because pentane would signify that those are alkanes with all single bonds, but we can clearly see there's a double bond here between carbons number 2 and 3. So one issue you want to take care of is this numbering system. Double bonds take priority over branches. That if I were to draw it this way, so here, I'm going to draw it 2 different ways. This is 2-pentene. And we put number 2 because that's where the double bond begins. The double bond begins on carbon number 2. So we signify that here and we put 2-pentene. If I put it, the double bond, let me put a double bond here. Well, just like our branches, we want the double bonds on the lowest numbered carbon we can put it on. So my numbering system here is going to be carbon number 1, carbon number 2, because 2 is the lowest numbered carbon we can put it on. If I were to do this, 1, 2, 3, well, my double bond is on carbon number 3, but we want it on the lowest numbered carbon we can put it on. So we're going to use this numbering system here. And again, we have 2-pentene. ENE. Triple bond. This is an alkyne, so we're going to use YNE. Carbon number 1, 2, 3, 4, 5, 6. So the triple bond begins on carbon number 2. The next one, 1, 2, 3, 4, 5, 6. Now we have branches here. Well, we already know how to name the branches. That's not an issue. But here, now this comes in the middle of it, this 3-hexene. But it begins on carbon number 3. That's where this double bond begins, on carbon number 3. So we do want to make sure that we note that. Right? The double bonds take priority in the numbering system here. So 1, 2, 3, 4, 5, 6, 7. Instead of calling it heptane, right? We drop the ANE and we add YNE because it's a triple bond. Carbon number 4 here has an ethyl group, so 4-ethyl, 2-heptine. And then we have what we call these Cyclo Alkanes here. So here, if we were to draw a structure like this, that this is cyclo cyclopentane. But then we have a double bond in here, making it cyclopentene. And if we add branches to it, again, the double bond takes priority. The double bond takes priority is that I know that we have these 2 branches here, but this one or this one is carbon number 1 because that takes priority in the numbering system over the branches. So if this is carbon number 1, carbon number 2, I'm going to follow that double bond, and this is going to be carbon number 3. Or we could carbon number 1, carbon number 2, and this is carbon number 3. Either way, with this one here, it's pretty symmetric, is that this one here is going to be, we're going to consider 3, so 4, 5, 6. So we have methyl groups on carbons number 3 and 6, dimethyl cyclohexene. So let's, you know what, let me get one more example here. I want to make sure we understand this numbering system. All right. Double bond takes priority. Triple bond takes priority in the numbering system. You want the double bond or the triple bond to be on the lowest numbered carbon you can put it on, which means that I have no choice but to make this carbon number 1, regardless of where my branch is at. Regardless of where that branch is at. So my numbering system is going to go like this, which means I have 5 bromo. I need to know where the double bond is, and it begins on carbon number 1. And it is, instead of saying that it's hexane, it's a double bond, so that's going to be called hexene. So 5 bromo, 1 hexene. A over here, I just numbered it here. I want the double bond starts on carbon number 1, so we're going to have 1. Instead of butane, we're going to call it butene because there's a double bond. Here's my numbering system over here. Here's my ethyl group. On carbon number 2, I have an ethyl. I need to know where the double bond begins, and that begins on carbon number 1. And this is pentene. I have a cycloalkane, but there's a double bond, so it's now a cycloalkene. if this is carbon number 1, this is number 2, and I have to number it this way here, which makes the branch carbon number 6, the methyl group. If I number it the other way, the methyl group's on carbon number 3, and that's a better suit. So this is going to be 3-methyl cyclohexene. And there's something we should notice here. Anytime that I have an open structure, one of these line structures here, this is not a cyclo, this is not cyclo, and I have to put the location of where that double bond is. In a ring structure, that's not required. This is not one cyclohexene. There's no number in there. It's just cyclohexene, because in a ring structure, it's always going to be carbon number 1. It's just like having one branch there. I don't have to signify that there's a, but I do have to signify it here because of this double bond there. So this is 3-methyl cyclohexene, not one cyclohexene.
Can there be more than one double bonds?
Not in this class here. We talk about those in organic chemistry, but as far as this class here, I will not put more than one double bond between carbons. We are going to see more than one double bond, but those are structures that were going to be something like this, is that we could see something like this. So there are 2 double bonds here, but there's only one double bond that sit between 2 carbons. We'll learn more about this next week, but that's the only time we would see that. Let's name this last one here. So we have 1, 2, 3, 4, 5, 6, 7. Methyl, methyl, methyl. So this is going to be 4, 5, 6. Trimethyl, where the triple bond here is located. So that's going to be on carbon number 2. And instead of heptane, because it's a triple bond, it is heptine. All right, let's name this structure here. This is carbon number 1. At the end of that is carbon number 2, 3, 4, 5. So this is pentyne, and we have 3 branches here. So we're going to have 3, 3, 4, trimethyl, 1, heptine. Everything that I've been giving you, everything that we've gone over so far, are what we call IUPAC names, right? They're IUPAC. So then we have what we call non-IUPAC. These are just what we consider common names. So here, this is IUPAC. This is IUPAC. And this is the common name, right? So common name, acetylene, ethylene, these are common names that we have. So if I were to draw something like this, we can name this 2 different ways here. The first one, let's name it using IUPAC naming convention. Well, 2 carbons is ethane, but because it's a triple bond, we're going to call it ethyne. This is carbon number 1, carbon number 2, and this is one branch. another branch. So here I have 1, 2. These are isopropyl, so di-isopropyl. So 1, 2 diisopropyl ethine. Or if we're going to use the common name, we can call it 1, 2 diisopropyl acetylene. We're going to get more into these probably next week in Unit 8, where we start to see a couple of different, we're going to use a prefix named form and another prefix with a seat. So we'll definitely see this more next week as far as using these common names. So this is just kind of an introduction. You may see something like this on your homework when they're talking about the common name of a structure using either acetylene or ethylene. And then you might see that in your homework. All right, so some more isomers that we have here. So more isomers are what we consider trans and cis isomers. These are structural isomers, right? But they are what we consider cis and trans. They're the same molecular formula. 2 carbons, 2 hydrogens, 2 bromines. 2 carbons, 2 hydrogens, 2 bromines. 2 carbons, 2 hydrogens, 2 bromines. The way that these atoms are bonded would either determine whether it's what we call cis or trans isomers. So these elements here, for us to have something that's cis or trans, the atoms have to be identical, right? These two are identical. There's 2 bromines here. And if we see them on the same side of the carbon, the same side of this double bond, we consider those cis isomers, right? If we see them across, where they're on opposite sides of that double bond, we consider those trans. So if I have a structure, we don't need to particularly name the structure right now, but let me put this double bond here. Well, this, because I'm looking at the double bond here, and I see this fluorine on the opposite side of this fluorine, is that this would be trans. And as far as cis goes, let me redraw this. Cis. I'm going to put the double bond here. And if we're looking at the double bond, we can see that these fluorines are on the same side. So this would be considered the cis isomer. So we can actually name, now that we know that they're cis and trans, we can name them accordingly. If this is trans, so let's find carbon number 1. Carbon number 1 is 1, 2, 3, 4, 5. So we have 2, 5, difluoro. The double bond begins on carbon number 2. And this is 5 carbons, pentene. And because it's trans, we're also going to signify that here as trans. So the name of this is trans 2,5 difluoro-2-pentene. Here we would have cis 2,5 difluoro-2-pentene. So we signify the isomer, which is cis or trans. We signify the location of the substitute or the branches here. And then we also have to signify the location of the double bond, and also signify here in the name that it's an alkene. So a lot of work really goes into naming some of these these complex structures here that we see as cis. But in order to be cis or trans, you do have to have a double bond. If I were to draw this, this is not cis or trans. And it's not cis or trans because I simply just I don't have a double bond. This is simply just 2,5-difluoropentane. There's no double bond, so I don't have to go pentene. There's no double bond, so it's not cis or it's not trans. That this is simply just 2,5 difluoropentane. Right? So we do have to have that double bond there in order to identify it as cis or trans.
I have a question.
Yeah.
On the cis 2-5, 2,5, why is it 5?
Oh, I'm sorry. It's not 2,5. It's 2,3.
Yeah.
Correction.
Okay.
Thank you very much. Let me make that correction. It is 2,3. 2,3. This is 2. 3. Sorry for yeah. I'm sorry about that. So yes, 2,3, 2,3, 2,3. The other situation, we do have some more cis trans. So the other situation we would have is something like I'm going to draw expanded structural formula here.
Does this only apply to double bonds?
Only applies to double bonds, correct.
Mm-hmm.
So I mentioned that we have to have two identical elements. Well, we do have a case here. There's no branches here. There's no alkyl. There's no halogen. But we do have two identical elements on both sides of that double bond here. This one is on the same side of it, and these are on the opposite side of it. But hydrogen is not a branch. So up here, if we look at this example up here, we put trans 2,3-difluoro-2-pentene. Well, because hydrogen is not a substituted group, we still have to recognize this as cis or trans. So here, we still recognize this as cis, but we're not going to say cis 2,3-dihydro. We're going to eliminate that part completely. I need to know the location of the double bond. Begins on carbon number 2. And that this is hexene. So this is simply just cis 2-hexene, and this is trans 2-hexene. Right? Because there is no substituted group here in order to name the rest of that there. So, and then in line formula, let me do this in line formula as well. So here it is in expanded and in line formula, where they're both either cis 2-hexene or trans 2-hexene.
So for these trans and cis, does it work for any kind of thing like ethyl methyl, or is it just like
Yeah,
the?
no, absolutely. Yeah, we can absolutely do that. Is that here? Um, let me draw it in line formula. Um, Actually, I could, you know what? I could just attach it right there. So here's my double bond. And actually, I'll do both of them here. But yeah, I could put a methyl group right here and a methyl group right here, and that would still be considered. This would be 2,3. This would be trans 2,3 dimethyl, right? I could put the methyl groups here, and that would be 2,3 or cis 2,3 dimethyl. Does that make sense? Yeah, so we get a little bit more advanced. You won't see anything like this on the exam. I wouldn't do anything like that on the exam, but you may see this. Say if you ever take general chemistry or organic chemistry, is that you would definitely come across situations like that, and some of them are named just slightly different. When we talk about rotation, that gets into some complicated topics, but nothing that we would see in this class. We would either see it with a halogen, or we would simply just see it with just the hydrogens and not consider any methyl or ethyl groups there.
I also have a question.
Yes.
Would this apply, the cis and trans, would that apply to triple bonds as well?
No, just double bonds.
Okay, well, thank you.
Just double bonds. Reactions. So I think probably about 10 more minutes, maybe 10, 15 more minutes. We're almost done. So reactions of alkenes. So on the exam, you're going to get tested on reactions, and you really want to make sure you understand these. So we've already gone over 2 reactions, and those are reactions regarding alkanes. These are reactions regarding alkenes. So they're all what we consider, they all kind of fall under the umbrella of addition reactions, where we're going to break one of the bonds in the double bond. Right? We're going to break the double bond and turn it into a single bond. So if we have, I'm going to redraw this with some actual hydrogens here. So here we have an alkene, and the AB could really be anything. The AB, this could represent AB. I know that they're both the same. It doesn't really matter that this is going to represent A, this is going to represent B, which means that I could also write it like this, right? If I were to write it like this, it just means that we have BR and BR, right? This is A and this is going to be B, right? That's all that it means there. So here, let's actually use some chlorine. So plus some Cl2, and then down here, actually, I'll just draw it out here, Cl2. Now, actually, you know what? I'm not even going to write Cl2. That's going to jump too far ahead here. But I will use A and B. So A and B. So here, what we're going to do is we're going to just break one of the double bonds. One of those is going to get broken. And if I break that double bond, well, I'm just going to redraw what I have. I broke the double bond. I have 2 hydrogens on the structure, and this carbon also has 2 hydrogens in the structure. And carbon, don't forget, right? One of the first things we learn is carbon needs 4 bonds. So what we're going to do is this also gets broken. A can go over here, B can go over here, or vice versa. B can go one and the A and the other one can go A. Doesn't really matter the order. So we can put A here and then we can put B over here. Or we can put B and then A. Again, it doesn't really matter at this point. So the next three reactions are all going to consist of the same concept. Break the double bond, break this double bond, and add your reactant. Break the double bond, add the reactant. So if we're looking, the first one is what we're going to call, this addition reaction is what we're going to call hydrogenation. We're going to add some hydrogen because it's a hydrogen right here. Hydrogenation reaction. We're going to add hydrogen. So normally we need some kind of catalyst, some metal catalyst, typically a transition element plus some heat. So that's all the stuff that you see down here. But again, we break the double bond and add the reactant. If we're looking at this here, I'm going to draw this in expanded structural formula so we get a really good understanding of what we're looking at. So here, each one of these carbons has two hydrogens, except for the one that contains the double bond. So except for the one that contains the double bond, those each have one hydrogen. Now we're going to add some hydrogen, and again, this is what we're looking at here, right? So H2, H2, we're going to break this double bond right here. I'm sorry, we're going to break this bond here, and we're going to break this bond here. We're going to use some heat, and we're going to use a metal in order to do that. And then I'm going to redraw it over here, but I'm going to redraw it without that double bond. I'm not adding anything to it. Only thing that I've done right now, or that I am doing right now, is I'm adding in the hydrogens that we currently have. So the only thing that I've done right now is I've broken the double bond. So now this hydrogen and this hydrogen have to be put somewhere. And I'm going to put one hydrogen here and one hydrogen here. And that's the same thing that we have here. We break the double bond and we add the reactant. Break the double bond, add the reactant. Every single hydrogenation reaction is done the same way. Here, this would not be a wrong answer. I would consider this right at this point. I wouldn't mark this wrong. But notice it's not required to write those in, because at this point you are expected to know and assume these hydrogens. If I point to this carbon right here, you need to know that there are two hydrogens there. We assume that because this is geometric formula. And we can see that if I'm pointing, look at two hydrogens on that particular carbon, we can see it. That here, we have to have an understanding that there's only one hydrogen there on that carbon. And look, one hydrogen on that same carbon. So if it doesn't have a double bond, I have two hydrogens here, two here, two here, two here, one here. And now if I look at my product, well, here there used to be just one hydrogen, but there's no double bond there, so I know that there are two hydrogens there now. I don't actually physically have to write that in there. I'm going to assume, because there's no double bond, that there are now two hydrogens sitting at this particular carbon. Here, instead of one, now it has two because there's no double bond there. You know what? No, let me use a different structure. I'll just use cyclobutene. So here's cyclobutene. I'm going to add some hydrogen to it because it's a hydrogenation reaction. I'm going to add some heat. I'm going to use some palladium, and I'm going to get this structure here. I broke the double bond and I added the hydrogen. How do I know I added the hydrogen? Because there's one hydrogen here, and here there's two hydrogens. There's one hydrogen here, and over here there's two hydrogens. Okay. So every single hydrogenation reaction is going to be done the same way. It doesn't matter if it can even do it like this. We can do it like this. Let me put this double bond here. Heat, a metal. I'm going to break the double bond and add the hydrogen. And there it is. Over here, I know there's one hydrogen, and here, I know there's two. Over here, I know there's two hydrogens, and over here, I know there's three hydrogens. So in fact, I did increase this by two hydrogens. So in line formula, it's very simple. We just break the double bond and rewrite the structure without it. The next one is what we're going to call reactions of alkenes. We did reactions of alkanes, right? If we go back to alkanes, here's halogenation of an alkane. We get this halogenated alkane with one halogen, and then we get a hydrogen with the other halogen. Well, this is now halogenation of an alkene. But it's the same process. Break the double bond, add the reactant, right? This is A, this is B, this is A, this is B, right? Break the double bond and add the reactant. How about, right? I'm going to break the double bond and I'm going to add the reactant. Break the double bond, add the reactant. Let's see, how about, as long as it's a halogen, it's always the same result. I'm going to break the double bond. So there it is. I broke the double bond. There's 5 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'm going to add the iodine. Wherever I broke that double bond is where I add it. What we don't want to see is this would not be an answer. Nope. I'm going to put one iodine over here, and I'm going to put one iodine over here. Well, that makes no sense because that's not where the double bond was at. We replace that double bond. Both of those double bond, or both the carbons involved in the double bond, are the ones that receive that particular iodine. So we wouldn't see a structure like that. Over here, I'm not going to put a chlorine over here and then put a chlorine over here, right? No. I'm not going to put both chlorines over here, right? So we wouldn't see a structure like that or like this, right? Wherever we break the double bond, that's where we happen to put it. How about this one? How about we work backwards? All right, so I need an alkene and I need a halogen in order to make this reaction happen. Well, I recognize that I have ClCl, so I guess Cl2 must be one of the reactants. And now I need an alkene. I need an alkene. This is an alkane. But wherever those chlorines are, that's where my double bond should go. So we can even work these in reverse, where if we have the product, we could determine this. So that's kind of something you want to watch out for in the lab, in the lab for lab 7. The last one here is what we're going to consider hydration. Right? Hydration, well, of course, we're going to be adding water because it's a hydration reaction, but we can't split this up. We have to split this up unevenly. So we're going to split this up into hydrogen, and we're going to split it up into some hydroxide. This will be considered A, this can be considered B, and we have A, and then we have B. So again, break the double bond, add the reactant. If I break this double bond, wherever I broke that double bond, I need to add A and B. Break the double bond, add the reactant. This would also be considered correct. Because it's hydrogen and we don't really have to write it out, this would also be considered a correct answer. But again, it's always the same way. Let's use right. Here's my alkene plus water. I need some kind of acid. Let me actually write it out with an acid here. How about we use sulfuric acid? So let's use sulfuric acid. We're going to break the double bond. So I broke the double bond. Hydrogen on one side, hydroxide on the other. All right. So now we have 5 reactions that we've learned so far. So with alkanes, it's combustion and halogenation, and then for alkenes, it's hydrogenation, hydration, and halogenation. So alkenes are done different ways as far as halogenation goes. There's 2 different reactions for that. And that gets us down to our last portion of here where we talk about aromatics. These are our arene rings, aromatics. So arene rings, this is benzene, and benzene is a very, very unique molecule. The energy level that a benzene ring has is very low. This is a really stable molecule. Is that it's very easy to remove one of these hydrogens and replace it with something else, right? But these double bonds here these are really strong double bonds. Like, we can't really break those double. Well, we can, but it just takes a lot of work. It takes a lot of energy to break that up. So either way you see it, it doesn't really matter where you put those double bonds as long as you go double bond, single bond, double bond, single bond, double bond, right? Double bond, single bond, double bond, single bond, double bond, single bond. Right? This is another acceptable form. Your books use this quite often. They use this because we actually don't know where those double bonds are, right? These double bonds that are in there are constantly in motion. Is that this one jumps over here, this one jumps over here, this one jumps over here, this one jumps here, this jumps here, this jumps here, and they're always rotating, and we actually don't really know where they're at. So this is why this one is also an acceptable form. I won't ever use that on my, I don't ever use those. I don't like this form, but it is an acceptable form. So this is, when you see this here, this is benzene. I mean, that's a horrible looking benzene. Right, so whenever you see this, you just need to think of benzene. Right? It's not, cyclotriene or something goofy like that. It's simply just benzene. You memorize it, this is benzene. Then if I were to add a branch to this, well, there's only one branch here, so I know it's carbon number 1. So we name the branch bromo, and then we attach the word benzene. So this is bromobenzene. If I have 2 branches, maybe I put bromine, and then let me put, let me put a methyl group on here. No, actually, let me put ethyl. Right. So here I have a bromine and I have an ethyl group on here. All right. Well, bromine comes first, and I'm going to mark this as carbon number 1. And I'm going to take the shortest path, and I'm going to go to carbon number 3. So it's not clockwise or counterclockwise. It's the shortest path. All right. So I have 1 bromo, 3 ethyl, benzene, right? Not 1, 3, 5 Cyclo Hexane or something goofy like that, right? It's just it's simply benzene, right? So 1 bromo, 3 ethyl, benzene. So anytime we have branches like that, we can just simply use that benzene name instead of cyclo, and then our alkanes that we named that way. And these are what we can consider benzene derivatives, right? This is a new one here that you may or may not see. So when you see NO2 as a branch, we're going to name that as nitro, right? So if I had NO2, then this would be 1, 2 dinitro benzene. So that's kind of a new branch that we look at here. And then there's a bunch that you guys need to memorize. So you guys are going to be memorizing, not these, because these are just easily named, right? The ones that you need to memorize are these. And there's an additional one in here. So as far as benzoic acid goes, there's a few variations of benzoic acid. These 3 all represent benzoic acid. And you have to memorize these, right? Is that when you see the structure like this is not methylbenzene. This is not hydroxybenzene. This, right? So these have special names because they contain functional groups on benzene. So you have to memorize these. So here, if we use this as an example, is that this is phenol, not hydroxybenzene. This is phenol. So this phenol here, if I were to put a branch on it, and let's put chlorine on there, this is going to be carbon number 1, 2, 3. I'm taking the shortest path. Actually, you know what? Yeah, well, I'll keep going now. I don't want everybody to keep thinking I'm always going clockwise. It's the shortest path, right? The shortest path. Is that here, I would, on carbon number 3, I have chlorine, so I'm going to call it chloro. But you have to memorize this structure, and it's phenol, not hydroxybenzene. So this is going to be 3-chloro phenol, phenol. It's all the same how you pronounce it. Tomato, right? So this is 3-chlorophenol, right? I could do one with aniline. Right? There's an isopropyl on aniline, right? So this is not nitro dihydrogen benzene, right? Nothing goofy like that. You memorize this structure as aniline. So here's carbon number 1. I'm going to take the shortest path. Carbon number 3, so I have 3 isopropyl aniline. 3 isopropyl aniline. Right. So that's how, but these have to be memorized. There's one more that's not on here that does have to be memorized, and that is benzaldehyde. And that looks like this. Or oh, that's a horrible sign. Right. So either way, you see it like that. These all represent benzaldehyde, right? One thing you want to be careful with, and I will point this out here. This if you, I won't stop anybody. I never use benzoic acid. I don't like it like this. I don't use that. When I write benzoic acid, is that I write it like this. I write it like this, or I write it like this. But I will not stop anybody from using this because it is acceptable. But be careful. There's a difference here. Actually, let me use the little circle. This benzoic acid, not benzoic acid. Can anybody tell me why this is not benzoic acid? Type it, unmute your mic, but can anybody see why this is not benzoic acid?
Is the bond not connected to the C?
Because the bond is not connected to the carbon. The bond is connected to the oxygen. So be very careful when you're using this, is that that bond has to go to the carbon. And whether you draw it like that, you could also draw it like this. It really doesn't matter where you put it. I could put it over here and go, COOH. And this would still represent benzoic acid, right? Then I could draw it this way, put it down here, COOH. I'll use the little circle inside this time, right? That still represents. So it doesn't necessarily have to be at the very top one, right? Is that this is carbon number 1 here? This is carbon number 1 here. This is carbon number 1. Wherever the functional group is at, is carbon number 1. So see how this way it's kind of off to the side? Here's carbon number 1. Wherever we have the functional group is where carbon number 1 is at. I think we're done. So that covers Unit 2. Let me stop the recording.